Now, let us see how we find a scalar potential function once an irrotational vector field is given. In this case, F is an irrotational vector field given as such, and we need to find phi, the scalar potential function, so that it satisfies this relationship. There are two methods of doing it. So, method 1, we will do it in the same way that we did the previous problem. So, F is equal to minus grad phi. Now, get the dot product of both sides, I mean with dr, dot product of both sides with dr. Now, we know what this is. Grad phi dot dr means d phi, right. Then you plug in F here for this one, dot plug in this one to dr. Now, get the dot product. So, I dot I will be, I mean I dot I is 1, therefore, this times dx, similarly this times dy, and 6 plus z times dz. Then here this is the catch. You identify the terms consisting of only one variable, like x squared dx is a term of that type, x times dx. So, I will combine both. In this case, we have only x. Here y squared dy contains only, I mean this term has only one variable. Similarly, 6 plus z times dz has z, but there are two other terms consisting of two variables, like this one, y times dx, x times dy. I put those two at the end. Now, you can straight away integrate them, or you can write them as a derivative of something. So, you integrate this term, you have x cube over 3, integrate this x squared over 2. So, it is a derivative of this. Similarly, you integrate this one, then write it this one as the derivative of y cube over 3. You can do the same thing with this one. Now, you can write this, now this is an exact derivative. You can write it as a derivative of something. Now, how do you find that something? Something can be obtained, like you take this one, just integrate with respect to this. So, y times x, so x y, you get that. After that, since d is linear, d operator is linear, you can put them in one d operator like this, right. Right hand side you have minus d phi. Now, integrate both sides. So, these two will go away, leaving this one in the left hand side. Here you have to introduce an arbitrary constant. Right hand side you get minus phi. Now, multiply both sides by minus 1, and you will end up with this, where c is an arbitrary constant. Now, the second method. Second method is totally different from this one. Here again you start off with this one. Now, plug in what you have for f, and in the right hand side you know grad phi is I partial phi over partial x, j partial phi over partial y, k partial phi over partial z. You have a minus sign in front. Now, by comparing the components of I, j and k, you can come up with three equations. Now, this is equal to partial phi over partial x, this is equal to partial phi over partial y, that minus sign will be there, this minus sign. Here you have partial phi over partial z is equal to minus 6 plus z. I mean you get the minus sign here, but I multiplied both sides by minus 1 and get these three equations. After that, this is how you do it. You take equation 1. Using equation 1, you find phi. Then using that result, you plug in those two results, I mean what you get for phi using the first equation, you use that result in equation 2 and equation 3 to figure out the unknown part in that expression for phi. Again, let me explain you. You use this one to determine phi. There is an unknown quantity, unknown part. To determine that unknown part, you use the other equations. That is how we do it. Now, you take the first one, first equation, integrate both sides, but with respect to x. That means, if you have any y or z or a function of x, y and z in phi, that will be vanished, because if you had a function like that, once you partially differentiate with it with respect to x, right. Say you have, for example, y z, a term like y z in phi. When you partially differentiate it, that will go away. So, when you want to figure out phi again, that arbitrary constant is not enough here. That you have to replace, that unknown quantity. When you partially differentiate this, there will be an unknown quantity that will be, right, that will be consisting of both y and z. Therefore, when you integrate it in x, leaving the other variables as constant. So, you have this one, you have x squared over 2 minus, you have minus yx, because y is a constant. However, since we are integrating with respect to x, because here in the when you get the partial derivative, if you had a function of y and z before differentiating this, now nothing will appear from that term in this equation. Therefore, you have to consider that. That means, when you that instead of an arbitrary constant, you have to introduce a function. This capital F has nothing to do with this one, right? F in terms of y and z. Now, you need to figure out what this is. Now, you take equation 2 and try to determine at least part of this one. Now, you plug in phi here. You have obtained a function phi. You use that in the second equation. So, you have this is equal to minus 6 minus y squared, right, this one. Now, when you differentiating this partially, this is 0, because it is free of y, this is 0. When you differentiate this with respect to y, you have minus x. When you differentiate with respect to y, you have f dash. This side you have minus 6 minus y squared. Now, these two will go away, leaving this one as minus y squared. Now, you integrate it. Now, you integrate with respect to y, right, because here the variable we considered was y. Now, when you integrate it, you have y cube over 3. Now, instead of an arbitrary constant, still we did not consider a function, sorry, the third variable z. Now, that is an unknown part still. Therefore, you have to introduce that function, a function of z. Let that be g z. Now, f y z is, has this form. Now, update this one. Now, you have this part in phi, right. Now, instead of capital F, you use this one from here onwards, right, from this point onwards. Now, using a and b, you can come up with this one. Now, this is little bit upgraded than this one, but still you have to do some work to determine this one. Now, this something that you have not used yet. Now, you use this one to determine that function simple g. Again, plug in that in equation 3, right. So, you will end up with this one. Right hand side is minus 6 minus z here, this one. Now, when you partially differentiate this with respect to z, this will be 0, 0, 0, 0, you have g dash z. Right hand side is this. Now, you can figure out g z by integrating this with respect to Z. So, you have minus 6 Z, this one plus an arbitrary constant. I put a minus sign just to go hand in hand with what we had in the previous method. Now, this is the latest version of phi, but we have obtained G Z here. Let us plug in that here, and from C and D you can, you have this expression for phi. Now, we have completely determined phi, but we have determined it in 3 stages, right. First with capital F, second with simple g, third time with arbitrary constant c, right. You can see that you can compare this answer with the answer we obtained in the using the first method, and you can observe that both answers are the same. All right. Now, after this point, we have to move to a new topic, that is line, surface and volume integrals. So, I will see you in the next video with line integrals. Okay, thank you.